Welcome to the Ontario High School video podcast series. We're looking in Chemistry 1 at Unit 9, and this is our second podcast having to do with the historical development of atomic theory. The learning standards that we're specifically addressing in this podcast are 9-3 and 9-4. So, welcome, and glad you're here. One of the easiest ways to organize the development of scientific theory is to use the time frame and the scientists who were involved in the discovery. In the first podcast, we looked at Democritus and Dalton and their postulates regarding atomic theory. Our next scientist with relevance to this discussion is J.J. Thomson. And our learning standard 9-3 is simply this: I can draw and label as well as interpret a diagram that demonstrates the observations that Thomson made during his set of cathode ray tube experiments. Cathode ray tube is commonly abbreviated to CRT. These experiments that led to the identification of the electron as a constituent part of the atom that is common to all atoms regardless of the type of atom, and explain Thomson's plum pudding model of the atom. Here is a diagram of a cathode ray tube setup that would have been typical of what Thomson used in his experiments. And my recommendation for you is that you pause the podcast at this point and reproduce this diagram on a sheet of paper in your notebook. And then once you've got that diagram ready to label, go ahead and resume the podcast. So I'll give you a few seconds or moments, however much time you need to do that, and then again, resume the podcast. So welcome back. Let's take a look at the diagram. At the very top, you see a high voltage supply. And this was necessary in order for these experiments to work. On the left-hand side of the cathode ray tube, you see a negative sign and the word cathode. And the cathode is a negatively charged part of this system. And the important thing here, you see like a metal disc there. And the metal disc is going to be the source of what are called cathode rays, which we later were determined to be electrons. And what's really important here is that it did not matter what the metal was. You could use gold, silver, aluminum, copper, zinc. It did not matter what the metal was used in the cathode. Identical cathode rays were produced. And this was one of the things that gave Thomson the idea that atoms of different elements have similar parts that make up those atoms, and so that's very important. On the other side, on the right-hand side of the cathode ray tube, you see an anode, which is the positively charged metal disc, and then above and below you see a positive plate above and a negative plate below, which shows there's an electrical field with the positive side above, negative side below. And then when you look at the stream of cathode ray particles, and these particles are what were determined to be electrons, you'll see that they bend toward the positive plate as they travel from the negative pole to the positive pole of the cathode ray tube. And this is what led Thomson to believe that these were negatively charged particles. So go ahead and make note of anything that you think is important from what we just talked about on your diagram, and we'll go on to talk about this in more detail. As we continue on in the podcast, go ahead and refer to the diagram that you reproduced. The cathode ray tube, again, is a glass tube in which most of the air has been removed. It used to be that these were referred to as vacuum tubes, and if you've heard that term, that's where that came from. And that has two metal plates on opposite ends of the tube, and the cathode is the negatively charged metal plate from which the cathode rays flow, and they flow from the negative side to the positive side. and that's the anode, the positively charged metal plate. When Thomson subjected the rays to an electrical field, what would happen, what he observed, is that the cathode rays deflected toward the positive part of the field. And again, a reiteration that this is what led Thomson to believe that the cathode rays themselves carried a negative charge. Thomson used a variety of metals as the cathode, and the cathode rays that were produced were identical regardless of the metal source. Thomson also did, as part of his experiment, he placed a paddle wheel inside the cathode ray tube, and from the behavior of the paddle wheel inside the cathode ray tube, he determined that the cathode rays themselves were actually a stream of particles, and that particle behavior was critical to the identification of the electron as a part of the atom. And so whatever the metal was, it didn't matter. The cathode rays, those streams of negatively charged particles, were identical. And from this, Thomson concluded that the cathode rays consisted of negatively charged particles that are common to all atoms, and these particles were subsequently named electrons. Thomson also used the amount of deflection of the cathode rays as they were attracted by the positive part of a magnetic field and repelled by the negative part of a magnetic field to calculate the charge to mass ratio of the electron. Note that he determined the charge to mass ratio. He was not able to determine either the mass or the charge, simply the ratio of the two. And this is one of the things that allowed eventually for the determination of both the charge and the mass of the electron. So Thomson is responsible for finding the charge to mass ratio based on the amount of deflection in the ray as he varied the strength of the magnetic field. As a result of his experimentation with cathode ray tubes, Thomson proposed a model of the atom, which he called the plum pudding model. And in it, he used the analogy of a pudding to propose that all atoms contained negatively charged particles, or electrons, set into a matrix of positive charge. If you think about if you've ever had yogurt with sprinkles, the yogurt would represent the matrix of positive charge, the sprinkles would represent the electrons, which were particles that were set into that matrix of positive charge. So the positive charge was spread throughout the entire volume of the atom, while the electrons were like plums, or you could use raisins or sprinkles or whatever you can relate to in this analogy, set into the matrix of the pudding. The plum pudding model of the atom was really the first attempt at trying to describe what the atom itself may have been like. It was a radical change in thought in science to even admit to the existence of atoms, and now Thomson has come out and said we think this is what an atom looks like, and so that needed to be tested. And the next individual who comes on the scene in terms of the history of the development of atomic theory is Ernest Rutherford, a British scientist. And the learning standard that will help us to understand what Rutherford did is this. 9-4, I can draw and label as well as interpret a diagram of Rutherford's gold foil experiment, including the process of the experiment, and compare and contrast the predicted results to the actual observations, which led to the invalidation of the plum pudding model and establishment of the nuclear atom. This is a diagram of Rutherford's gold foil experiment, and this is one of the most elegant, important experiments in scientific history. If you would pause the podcast and reproduce the diagram of this in your notes, and then resume the podcast when you're ready, and we'll talk about the pieces. One of the pieces you'll notice is the lead block, and the lead block has cut into it an aperture or an opening for alpha particles to pass, and the source of the alpha particles was a small sample of uranium. There was some knowledge of radioactivity in this time, and though scientists did not know precisely what alpha particles were, they knew that they were high energy, positively charged particles, and they were put off by uranium, so that's why they used it. And they put it inside the lead block with just that tiny opening so that they could direct the stream of alpha particles toward the gold foil. And the gold foil, if you think about aluminum foil, metals, one of the properties of a metal is that they're malleable, meaning you can pound them into flat sheets. And the advantage of using gold metal is that gold is more malleable than aluminum, which you're familiar with, and most other metals. And you can pound gold into incredibly flat sheets, meaning from what we know now, just a few atoms thick of gold in that flat sheet. Around the gold foil, there was a fluorescent screen put up, and you'll see it says that it was a zinc sulfide screen. And what will happen is when the alpha particles strike the screen will fluoresce or light up. So as they watch the experiment occur, they can record where the particles are hitting. And that is what they wanted to do with that. And so that's basically the experimental setup. As we continue to talk about this experiment, be sure to refer to your diagram. Rutherford had these expectations. He did the experiment believing that he would confirm the plum pudding model of the atom. He thought it was very plausible. Since the positive charge was distributed throughout the entire volume of the atom, Rutherford thought that the alpha particle, which was high energy but positively charged, would blow right through the gold foil like a cannonball blowing through tissue paper, is what he expected. Because he did not think the positive charge in the atom was concentrated but rather diffused throughout that volume, he thought there would be very little resistance to the positively charged alpha particle going through it. Well, here are the actual results. Most of the alpha particles passed through the gold foil undeflected. Some were deflected slightly, and a few were deflected a great amount. This was not what was expected. They expected them all just to blow right through, mostly undeflected, and this surprised them greatly. So here are the conclusions that Rutherford came to as a result of the gold foil experiment. He believed that most of the alpha particles pass through undeflected because the atom consists mostly of empty space. 99.9% of the atom, in fact, is empty space. Because of the amount of deflection of some of the alpha particles, he concluded that almost all the mass of the atom is concentrated in a small, dense, positively charged center that we call the nucleus. The amount of deflection and the energy with which the deflected particles struck the screen was such that Rutherford concluded that the positive charge was not spread throughout the atom, but instead was concentrated in what we now know to be a small, dense, positively charged center. And this is the discovery of the nucleus and the beginning of our understanding of the atom as being a nuclear atom. So it's very important that you share these conclusions for Rutherford gold foil experiment, that atoms are mostly empty space and that almost all the mass of the atom is concentrated in that small, dense, positively charged center that we call the nucleus. Continuing with the conclusions from Rutherford's gold foil experiment, the electrons are not embedded in the nucleus. Otherwise, the nucleus would be neutral and would not have repelled any of the alpha particles. Rutherford suggested that the electrons might be circling or orbiting the positively charged nucleus, But this experiment itself did not provide a basis for this conjecture other than the fact that the negatively charged electrons were not in the nucleus. We've reached the end of the second podcast having to do with the historical development of atomic theory, and I'd like to leave you with a thought from the great novelist Flannery O'Connor. I don't deserve any credit for turning the other cheek, as my tongue is always in it. I wish you well.